So now we will investigate the expression of torque in terms of this in that in line with our previous discussion of primitive machine. So in order to deduce the expression for our torque, what it is necessary for us to first understand same or means even you know this approach what we did in case of when we analyze that energy stored in a or electromechanical energy conversion. What is the total amount of energy given to a system, and then from that what is the amount of energy stored inside that system, or how much amount of energy is raised in terms of system energy level, and the residue amount of energy, definitely that residue should be converted in form of some other, if you consider torque in form of mechanical energy. So it is there. Now, in order to deduce this expression, what we need to know that what is the first we have to find out the value of energy stored in a magnetic field. However, here we will neglect saturation and hysteresis. Here I would like to make it more specific. Hysteresis, nonlinearity effect. That means whatever amount of reversal we get due to, means we get or we realize or experience the effect of hysteresis, especially during reversal of current or flux through our, better to say flux through our system. Here we are considering that the system is hysteresis type nonlinearity free. It is just like that how we derived the equivalent model of our transformer, where we consider that the system is free from that nonlinear effect, otherwise we couldn't draw the phasor diagram. But neither way we are totally ignoring it, rather we would like to replace its means contribution in terms of energy dissipation in form of a equivalent resistor. We never claim that we are totally ignoring hysteresis. Had we ignored it completely, then there would have no that R naught would not means we could drop that R naught from our equivalent representation. And if it is like if we consider it completely, then we couldn't even draw the phasor diagram, because we know that for nonlinear system we cannot draw it. So it's a mix and match. We consider some part and we neglect some part. Now another thing is that magnetic energy is dependent only on the inductance and current at the instant we considered it. Now let us consider that let us consider a case. Suppose the inductance are first so adjusted So suppose that the inductance are first so adjusted that means what I am trying to say, that what we did in case of our magnetic circuit analysis, say whatever be the current means in your I lambda plane, or in other way lambda dash probably, or in case of your it was lambda x probably. So what we used to do, we used to integrate along one axis and then we try to consider the other axis. We could do it because we considered it as a circuit that is having no energy loss, right? Therefore, the path of integration becomes independent of our means uh, traversal. So here, however, the what we are doing, that we are we are doing what that in but then again the question is there that we cannot ignore the resistance also, but the answer lies, uh, which I said during that time also, that no one is asking you to consider or disregard the inductor resistance completely. We are just considering that whatever effect, suppose some impurities is there in your inductor or some hysteresis is taking place inside your inductor, we are considering them as a separate lump element and we place them outside of our inductor, right? So that they do not affect the reversal. This is what we are thinking about or we want to say. Now, here, as this, so therefore, the inductor, the model we are considering, that is lossless. That is very important. So the total process, we can write the equation like V is equal to Ri plus PLI. And if you consider that inductance is constant during the entire process, it will become V is equal to Ri plus LPI. So for a 3-winding system, we can write it will become like V1 is equal to R11I1 plus L11 di1 dt plus M12 di2 dt plus M13 di3 dt, right? And the same thing must be repeated for the other two phases as well. Only thing what we need to consider here is that right, and here it will be so this is the total structure we can have here. Obviously, we can slightly shift them here and there to get a good looking structure that all the self term appear in a diagonal position. That can be done. I am not much concerned about that. So if you do this, like if you do now, you will get now among them, if we consider, then these terms, these quad terms, they are indicating the three winding power dissipation due to that current. So the machine is raised, therefore the remainder power, the residual amount of power, must be stored in the mechanical field. So how can we write that? right? Obviously here it should be like di1 by dt, di2 by dt, di3 by dt. So other way what we can do is that as they are constant, we are assuming that this matrix is constant, we can take help of operator. And what modification we can do from this, like we can replace this di1 dt like this way. So in that case, what you need to do is that you need to consider here P, here P, here P. Or other way, what you can do is that you can instead of mentioning P here, it would be more rational if you mention P here, like all the elements. Now another thing what we can do is that we can exploit the balanced winding symmetric nature. So that would give us, so therefore the total energy storage would become what? Let me copy it in the other page. Just a minute. Well, so it will become something like right? We can write this, and obviously further one step if we proceed, what we will go get, that the whole equation can be instead of 3di2. Right. So in matrix form, we can write, now in our matrix form, what we can write is that we can write it like this way. 2 3 L 3 3. So this gives us half. This is a vector I comprises all this. So from the equation, we will get now R is a diagonal matrix, and therefore the scalar ITRI also we can write it like in this form. Quite often this n is 3. Right. Now, as we are considering at the onset, the system is stationary. Therefore, there is no mechanical power output, and the input power is I transpose V, and can only be dissipated as heat, or it can be stored in our magnetic reservoir. So, the stored energy, therefore, will be this much. Now clearly this I transpose L dt is again a scalar and is therefore equal to its own transpose, that is means we can means change the order, because L is a you can say L is a square matrix, and the two sides are the vectors of having equal dimension. So this can also be written like I transpose L di dt, the whole transpose, sorry, we will get now do note that L is symmetrical, so L is equal to L transpose. Therefore, this can be replaced by ordinary L, right? So this again give us, if you solve this integration, you will get now we need to figure out the torque expression. What is the torque expression? Like we have to figure out it from that fact V is equal to Ri plus PLI, where when you are talking about torque expression, you are no longer able to make it completely free. Like previous case, all the time you cannot make L constant, consider L constant and make it free. You can apply your concept of moving moving iron instruments, and you can easily understand this concept. So now consider this system during the movement from an angular position. Plus delta theta. Now all currents being maintained constant by our appropriate terminal voltage V. Now since the current is constant, therefore exactly what happens in case of your moving iron instrument, in most of the case you figure out that it is the current that remains constant, but whatever the voltage, the inductance, that changes with time. So however, if current is constant, then what you will have? You will have however, here these L, these R, they are not single element, they are representing a matrix, right? And therefore it is not as easy as writing d dt for normal Li. We can easily write that it is becoming I dl dt. Do remember here this one is suppose it is having a dimension n cross n, this is having a dimension n cross 1. So as this one is having n cross n, this one is having n cross 1. So writing n cross n into n cross 1 is not same as writing n cross 1 into n cross n. Neither this is matrix multiplication is conformable. So this form is what we can do for scalar case, as in case of moving iron instrument. The same thing cannot be applied here. We need some modification. So let us again go back to our three winding case, and just let me copy it. Well, then what we will have now, current is independent of our change, so we will have, however, these are scalar, this L11, these are scalar. Sorry. right? So if we multiply both sides, actually the same thing that you got in case of if you just read the expression of your moving iron instrument, the torque expression, almost similar things we are going to get here. Only change is that here instead of one we are having many windings. If you are wondering that why Sir is writing so many things, what is the essence of writing all this? Do remember that in your exam, I may ask you to prove a few of these. So make sure you are well prepared to uh, do all this for your son. So these are the power dissipating term. So again, if we subtract them, they do not contribute in torque production. However, the remaining term, this system is moving and the residue amount includes both power that could be stored in magnetic reservoir and power that may be converted in form of mechanical energy. So the sum of the increase of stored energy and the energy converted, this total is thus what? The total is thus so this gives us Right. So this gives us so the initial energy that was stored in our system, that is so this gives us square L11 plus half square L22 half I3 square L33 I2 M12 plus I2 I3 M23 plus I3 I1 M31, right? And the final energy will be how much? The final stored energy M31, right? Now Well, so this gives us what? This gives us that it would be like the increase of stored energy that could be written by this formula. Right. Now you will, if you notice mindfully, then you will find this is that exactly half of the sum of the increased stored energy and the energy converted to the mechanical power. Right. So it follows that the energy that could be converted to mechanical power is how much. This you will find is like, actually you will find that this is the same amount. So instead of writing it once again, just let me copy it once more and paste it. So the angle turned through this, if the angle turned through this is delta theta, then the mean torque is how much? The mean torque is, correct. Now, if we put the limit that delta theta tends to 0, then all these will become partial differential, like half I1 square del L11 del theta plus half I2 square 12 del theta half I3 square del L33 del theta. right? So in the form of torque matrix, what you can write is that half I1, I2, I3 2, 3, then here one, two, three, one, two, three, one, two, three, I1, I2, I3, del L11, del theta, del M12, del theta, del M13, del theta, del M12, del theta, del L22, del theta, del M23, del theta, del M13, del theta, del M23, del theta, del L33, del theta. So this gives us half I transpose del L del theta I. Right. So in our next video we will continue from this, that how we can deal with this and what similarity transformation can be applied on this particular thing.